Good morning, dear respected teachers and dear students. I am Kishor and I will discuss the Cauchy's residue theorem. Starting the explanation of this theorem, I will shortly discuss about Cauchy's integral theorem. Uh, in Cauchy's integral theorem, Cauchy says that if any function fz is analytic inside closed curve C, then the integration of the function fz is equal to 0. Cauchy modify the integral theorem into residue theorem and gave a statement that if fz is analytic function inside and on a simple closed contour C, except at finite number of poles z1, z2, zn inside C, then the integration of fz is equals to not equal to 0. It gives some values, that is 2 pi I into r1 plus r2 plus dot dot rn, where r1 r2 rn is residues. Here the function fz is analytic inside closed curve C but not analytic on the point z1 z2 zn. This point z1 z2 zn are the called poles where fz is not analytic. It means poles is the point where the function is not analytic. When function is not analytic on this point, then we will get some value, that is 2 pi I into r1 plus r2 plus dot dot rn. r1 is residue corresponding z1 and r2 is the residues corresponding z2, rn residues corresponding zn. Now we will discuss about how to find residues. This gives three type of formula to find out the value of residues. When the number of poles is simple order like 1 2 3, then we will use this formula. And when the number of poles is order 2 or order n, then we will use that is 1 upon n minus 1 factorial d to the power n minus 1 upon dz to the power n minus 1 into z minus a to the power n into fz. And when the number of poles is order of infinity, then we will use the formula residue is equals to limit z tends to infinity minus z into fz. Now we will discuss some questions basis of these three type of formula. The question is, find the order of each pole and residue at it of 1 minus 2z upon z into z minus 1 into z minus 2. Here given function is that 1 minus 2z upon z into z minus 1 into z minus 2. In this question we will find out the value of residues of this function. Solution. Let's take the denominator of the function is equal to 0, then we get z equal to 0, z equal to 1 and z equal to 2. This is 0 1 2. This is in simple order, all are simple pole. Here then we will use the first formula, that is r is equal to limit z tends to a z minus a into fz. So the first residues corresponding z is equal to 0 is that limit z tends to 0, because of the value of a is 0. The value of a is the value of z, a is equal to 0. So the first residue r1 is equal to limit z tends to 0, here z minus 0 into the function, the given function as it is. This z is this z cancel. Now put z equal to 0, then we get 1 by 2. and the second residue is limit z tends to 1 because of z is equal to 1. Here a is equal to 1, so we will put a is equal to 1. Limit z tends to 1 z minus 1 into the function. Now here z minus 1 to z minus 1 cancel, so when we simplify we get 1. After that the third residue is equal to limit z tends to 2 for the third pole z equal to 2. Limit z tends to 2 z minus 2 into 1 minus 2z upon z into z minus 1 into z minus 2. When we simplify we get minus 3 by 2. This cancel, so r1 is equal to 1 by 2, r2 is equal to 1, r3 is equal to minus 3 by 2 are the residues for this function. Now let's take a second question. Find the residues of the given function f(z) is equal to z square minus 2z upon z plus 1 whole square into z square plus 4. Now let's take same process. The denominator of the function is equal to 0, then we get z equal to minus 1 and z equal to 2 iota minus 2 iota is equal to minus 1. This is repeated value of the pole, then this is order up to, then for this pole we will apply the second number of formula, that is r is equal to limit z tends to a 1 upon n minus 1 factorial d to the power n minus 1 upon dz to the power n minus 1 into z minus a to the power n into function, and z equal to 2 iota minus 2 iota. This is in simple order, so for this pole we will use simple formula, first formula. Now in this formula the value of n is equal to 2 because of pole is equal to minus 1. This is repeated value. How many times is repeated? So 2 times repeated, so the value of n is 2. Now for the residue we will put up the values. So limit z tends to minus 1 because of a is equals to minus 1. Here we will use only one value of pole, so 1 upon 2 minus 1 factorial into d to the power 2 minus 1 upon dz to the power 2 minus 1 into z plus 1 to the power 2 a square minus 2z upon z plus 1 whole square into z square plus 4. After this when we simplify this term we will get limit z tends to minus 1 upon 1 factorial d by dz z square minus 2z upon z square plus 4. This term is differentiable. This is one time differentiation. Now limit z tends to minus 1. When we differentiate this term we will get this term. Here the denominator, first I write denominator into the differentiation of numerator minus write numerator into differentiation of denominator upon the denominator whole square. So after simplification we get minus 14 by 25. Then z is equal to 2 iota minus 2 iota. We will find second residues corresponding z equal to 2 iota. This is simple order, it is simple pole. Then we will use first formula limit z tends to a z minus a fz. So the residue is equal to limit z tends to 2 iota z minus 2 iota into z square minus 2z upon z plus 1 whole square into z. Now limit z tends to 2 iota z minus 2 iota into z square minus 2z upon z plus 1 square. Z square plus 4 will be z plus 2 iota z minus 2 iota, and z minus 2 iota to z minus 2 iota will cancel. So when we put z is equal to 2 iota, then we get this term, and after simplification we get this term. Now the third residues corresponding minus 2 iota. So using the formula limit z tends to a z minus a fz, we get this type of limit z tends to minus 2 iota z plus 2 iota z square minus 2z upon z plus 1 whole square into z square plus 4. After that we get limit z tends to 2 iota z plus 2 iota z square minus 2z upon z plus 1 whole square, and z square plus 4 will be this type, z plus 2 iota into z minus 2 iota. Z square plus 4 will break into two pieces, z plus 2 iota into z minus 2 iota. Now z plus 2 iota will cancelled with z plus 2 iota, and minus 2 iota putting in this term, then we get minus 2 iota whole square minus 2 into minus 2 iota upon minus 2 iota plus 1 whole square into minus 2 iota minus 2 iota. Then we get this answer here. R1 is equal to minus 14 by 25, and R2 is equal to minus 4 iota upon 2 iota plus 1 whole square into 4 iota, and R3 is equal to 4 plus 4 iota upon minus 2 iota plus 1 whole square into minus 4 iota. Now let's take a third question. Solve the question using residue theorem. The given function fz is equal to integration c 1 minus 2z upon z into z minus 1 into z minus 2 dz, where mod of z is equal to 1.5. The denominator of the function z into z minus 1 into z minus 2 is equal to 0, and get z equal to 0, z equal to 1, z equal to 2. These all are simple pole. Now the first residue is limit z tends to 0 corresponding z equal to 0, z minus 0, 1 minus 2z upon z into z minus 1 into z minus 2. This will be 1 by 2, and R2 will be 1, and here the residue R3 corresponding z equal to 2 is 0 because of the given mod of z is equal to 1.5, and the third pole is z equal to 2. 2 is the greater than 1.5, so that this pole is not lie in the closed curve. This pole is outside of closed curve, so that the value of third residue corresponding z equal to 2 will be 0. Then we know that the residue theorem integration c fz dz is equal to 2 pi I r1 plus r2 plus r3. Putting the values in residue theorem, integration c, the value of fz is 1 minus 2z upon z into z minus 1 into z minus 2 dz is equal to 2 pi I. R1 is equal to 1 by 2, R2 is equal to 1, and R3 is 0. So we get 3 pi I. 3 pi I is the answer of this question.